Hello and welcome to my YouTube channel. In this playlist, we are discussing about operational amplifier circuits, and today we are going to see how to design and analyze positive and negative voltage sources. So in this video, I will show you how to design positive voltage source circuits using operational amplifier. Then I will talk about the techniques to analyze positive voltage sources, and by the end I will show you a simulation in which I will show you the parameters which are very important in the voltage source circuits designed using operational amplifiers. First question that should come to our mind is, what is voltage source? Ideally, voltage source is a circuit which should provide constant voltage even if the load is changing, or we can say for any particular load the voltage source should be able to provide constant voltage, which in real life is not possible. Therefore, practical voltage sources are circuits which can provide constant voltage to certain range of load. When we are saying load, these are the devices which will consume current from the voltage source. One very important feature of any ideal voltage source is that the internal impedance of the voltage source should be 0. But practically, again, we cannot design, or we are not able to design voltage sources with internal impedance equal to 0. Therefore, practically we try to keep the internal impedance as low as possible. Basically, there are two types of voltage sources. One is independent voltage source, which is represented by this symbol, and it can provide constant voltage even if any other parameter in the circuit is varying, be it the load, be it the temperature, or any other parameter. So independent voltage source will provide you constant voltage even if any other parameter in the circuit is varying, or we can say it is nothing but an ideal voltage source. Second type of voltage source is dependent voltage source, which is represented by this particular symbol, and such voltage sources are dependent on or are actually controlled by some other parameters in the circuit. So let me first start with the first design to design a positive voltage source. So here you can see we have the voltage VCC, then R2, R1 and VEE. So I can drive this particular node voltage, or I can change this particular node's voltage by changing the resistance R1. This node, or the potential dividers node, is directly connected to pin number 3. So we will get V3 here at pin number 3. By virtual ground property, we know that the voltage V2 will be always equal to the voltage V3. And V2 is directly connected to pin number 6, which is Vout. And there is no feedback resistance to control the gain. So therefore, this particular configuration is unity gain amplifier, or you can call it also by the name buffer. Okay, so the gain of this particular configuration is 1. So whatever is the voltage V3 will appear at the Vout. Okay, and even by changing the resistance R3 to a certain limit or certain range, we will find that the voltage Vout remains constant, because by the virtual ground property. So this way we can design a very simple constant voltage source using operational amplifier. Now coming to voltage source designs with high output current. Remember, operational amplifiers cannot provide you high output current. In general, they can provide up to 20 milliampere current. But 20 milliampere current is not sufficient to drive a motor or a series of LED or any other high load which requires more current. For that, we can use transistor in the circuit. So again, here we have the potential divider circuit in the left, and V3 is again controlled by the value of R4, and by virtual ground property, V2 will be always equal to V3, and that voltage will appear here at the VE. Okay, voltage at the emitter. So depending on the value of V3, the voltage output will change or increase or decrease. Depending on that, the IB will change, increase or decrease. Okay, and we know that IC, that is collector current, is nothing but beta times IB. So if the IB increases, IC will increase. If the IB decreases, IC will decrease by a factor of beta. So the current IC will flow. Here I am using ammeter to show you how much the value of current we can generate using this particular configuration, and the current will flow in this direction towards the load, and the load voltage will be always constant, VE, because of the virtual ground property of the op-amp. Okay, so VE is nothing but equal to V2, and it is equal to V3. So we'll be generating a constant load across the load, constant voltage across the load, and IC we can vary by the BJT. Next, in this circuit, we are going to design voltage source using Zener diode as a reference voltage. So Zener diode, we know that even if the supply voltage is fluctuating by a certain amount, the Zener diode will keep a stable voltage across the Zener, which is given by Vz, which is equal to the breakdown voltage of the Zener diode. In this example, I am using a Zener diode of 4.7 volt threshold. So this node will be always equal to V threshold, which is equal to 4.7 volt. So Vz will appear at pin number 3, and again by virtual ground property, V2 will be equal to V3, which is equal to Vz. So V2 is nothing but equal to Vz, and Vz will appear here also because pin number 2 is directly connected to this node. Now, if assume I represent this node as V0, then V0 will be dependent on Vz and R2 and R3. To derive the value of V0, we can use nodal equation. So Vz minus V0 divided by R2 plus Vz minus 0 divided by R3 is equal to 0. And by simplifying that circuit or simplifying that equation, we get V0 or V output across the load RL is equal to Vz multiplied by R2 plus R3 divided by R3. So in this way, we will be able to provide a constant voltage V0, which will be dependent on constant voltage Vz or the breakdown voltage of the Zener diode, and the amount of current can be varied by changing the value of R2 and R3. So now let us look into some of the simulations or the simulations of the circuits which are being discussed earlier. So here we have the voltage VCC, R2, R1, and we will get a voltage V3 which will be dependent on the voltage of or dependent on R2. By varying R2, you can see by varying R2 I can vary the value of V3. Okay. Now by virtual ground property, the same value will appear at pin number 2 you can see here 6.67. Even if I change this voltage, you will get the same voltage by virtual ground property. And this voltage is appearing at V output. So 8.52 volt is appearing at the output. And even if I change the load resistance R3, you can see the voltage is constant. V out is constant for a range of R3. But if I drop the R3 by a very large amount, you can see the voltage V out may change. Okay. So for a certain range of resistances, we can generate a constant voltage at V out. This was our first circuit. Now let us go to the second circuit to generate higher output current. So here you can see we have almost the same configuration, VCC R5 R4 making the potential divider, and the voltage at pin number 3 is 9.45 and it is the same at pin number 2 by virtual ground property. And this same voltage will appear here by the virtual ground property. To change the amount of current, we can vary the value of R4. Okay. And you can see we are reaching somewhere around 26 milliampere, and we can further change the value of current IC by changing the value of R4. So in this way, if we need higher current, we can use the voltage, constant voltage and higher current using BJT. Now coming to the last circuit using Zener diode voltage. Here we have replaced the resistance from the potential divider with the Zener diode with the breakdown voltage of 4.7. So pin number 3 will get 4.7 volt. Okay. And the same voltage will appear at pin number 2 by virtual ground property. So you can see here both node V3 and V2 is equal to 4.7 volt. And 4.7 volt is actually appearing at VZ also. So if you see here at the voltage output, V0 is dependent on VZ and the value of R2 and R3. So by changing the value of R3, I can change the value of the load voltage. And even if I change the value of load resistance, we can see the voltage, output voltage is constant. So therefore, we can generate a constant voltage across the load RL, even though I am changing the load voltage by a very large range of values. So in this way, we can generate a very precise constant voltage across the load RL and provide higher current by the virtue of transistor or BJT. And this circuit can be used to design any circuit in your future projects if you need a constant voltage and higher current. Only thing is you have to choose the value of Zener diode breakdown voltage according to your choice. With this, I end up the lecture and I hope you liked this video. If you have any suggestions or comments, then please put your comments and suggestions in the comment section. If you have not subscribed the channel, then I would request you to please subscribe the channel. Thank you and have a nice day.